Okay, so this is the condition that we should somehow satisfy.
Yeah. And the left-hand side, I think like a Fourier transform of the derivative of f.
But there's also 1 over omega, so it's like Fourier transform of f.
Well, that 1 over omega is on both sides. So that 1 over omega, in fact, we can cancel on both sides.
Okay.
Okay.
And the Fourier transform of the derivative is omega times the norm of the Fourier transform of f.
So you are, okay, first of all, are you taking a function f that is valid from minus infinity to infinity?
Actually, I assume t to be.
If you are assuming t is periodic,
I assume t is very large, but I didn't want to remove it.
okay, so you are saying that it is f times omega. Well, in fact, that is what we actually used here. Well, where was it? You see, when we were taking the integration by part, that is what we used. Okay, so it's omega times f.
And it should be less than the normal function.
Omega times f should be much less than f.
Yeah, but the first f is the Fourier transform.
Fourier transform itself is much smaller than itself.
Well, omega
Omega times the Fourier transform should be smaller than the original function.
okay.
And if the original function has very high frequencies,
Well, you see, the original function, we are saying that the derivative is small, so it should be more or less constant.
yeah, if it's
So it cannot have
then
it cannot have high frequencies.
okay, if it has very low frequencies, then Fourier transform is located near origin,
Okay.
so its value should be large.
Omega times f of omega should be less than f of t, right?
So,
You're multiplying with the frequencies.
and
So-
also if it has very low frequencies, then the t will not encapsulate multiple periods, so you cannot think it is a Fourier transform.
But even like this, you see, f is almost constant. So f of omega is almost 0 unless omega is very close to 0. But omega is a fixed value. Omega here is equal, h bar omega is em minus en, which is non-zero. But in fact, that condition can be almost trivially satisfied. That condition will be almost trivially satisfied if f is almost constant. Or we can say that if that condition is satisfied, then the derivative of f will be small.
But here, omega is a constant value, right?
Yeah, omega is well, let's see, omega is not really, well, you see, n is constant, m is all the other states. So omega can have many different values.
Tracing.
Yeah, it is tracing. So omega has a gap. It cannot be 0. That's where we are assuming that there is no degeneracy or approximate degeneracy. Omega is large. There's a gap between omega and 0, and omega can have various values, and this condition should be satisfied for all omega. Omega can be very large. But if omega can be very large, that means f of omega should be very small. So the Fourier transform of omega should only have non-zero values for small values of omega. So this is what this condition is about. But if f of omega is non-zero only for small values of omega, that means it's mainly a constant.
But then
Its derivative is small.
But if it is like bandwidth, so its values at low frequencies should be large.
Okay, so, but I'm multiplying it with a small number, which is omega. But you see, as long as you say that f of omega should have values only for small values of omega, then we are done. Our proof is done. And this cannot be satisfied for large values of omega. And in fact, this is, by the way, we assume to be 1.
Actually, I think we can find some functions that satisfy this condition and has non-zero values at high frequencies.
Okay, homework for you. Well, of course, you have to also show that for those functions, this integral can be treated as a Fourier transform.
It is like for high frequencies, it can easily be interpreted as Fourier transform.
For high frequencies, it can be treated as a Fourier transform because the exponent is oscillating very fast. Since the exponent is oscillating very fast, you can take the limit to infinity. You won't receive any contributions from large t. You see, what you are saying that for large frequencies or for large delta E, this can be treated as a Fourier transform. That's what you said, right?
Yes, I think so.
Okay, it can be, I'm confirming you, because if delta E is large, very large, for large values of t prime, the exponent is oscillating very fast, so we are not receiving any contribution from them. Since for large values of t prime we are not receiving any significant contribution, then we can easily take the upper limit of the integral to infinity.
Yeah, okay. I thought it was much more simple.
I would say this is simple. I would say my explanation is also simple. Other questions, comments? Let's do an example. Electron in a magnetic field. Now we will just assume that, okay, this is the z-axis. We will take a magnetic field that is rotating around the z-axis. That will be the problem we are studying. And if the rotation is small enough, is slow enough, so if we start with an electron at t equal to 0 in the direction of the magnetic field initially, what we should get is at a later time the magnetic field should be, the electron should be rotating with the magnetic field continuously. So that is what we should drive. Well, this is also an exactly solvable problem. So let's see if that assumption is correct. B of t, okay, there is the V0 cosine alpha in the z direction. This is fixed, but the x and the y components, they just rotate. So we will have B0 sine alpha cosine omega t in the x direction plus sine omega t in the y direction. This is my magnetic field. Well, the Hamiltonian for the system will be just minus q over m b dot s. Now, if you remember, it was q over 2m times the gyromagnetic ratio. For the electron, g is just 2 and q is equal to minus e. So we have the Hamiltonian, which is e over m b dot s, or h bar over 2m b0 times cosine alpha sigma z plus sine alpha cosine omega t sigma x plus sine alpha sine omega t sigma y. Or we can also write it in the matrix form. This will be equal to e h bar over 2m b0 cosine alpha minus cosine alpha. This is the...
Does it rotate like a cone?
Yes, the magnetic field just follows the cone. Minus cosine alpha, sine alpha, e to the power minus I omega t, sine alpha, e to the power I omega t. So what are the eigenvalues of this Hamiltonian at a given time t? But at a given time t, the Hamiltonian is in fact nothing but e over m times b of t times the spin operator in the direction of b of t. Right? No? So this operator has eigenvalues plus or minus h bar over 2. So I can easily say that at the time t, the eigenstates, let's call them plus or minus, these will be plus or minus h bar or e over 2m b of t. Are you convinced?
This is the eigenvalue.
This is the eigenvalue of the Hamiltonian at the time t. So in a sense, e of t, e plus or minus of t, this is equal to plus or minus h bar e over 2m b of t. Well, let me also put some time dependence over here. Now, what are these chi? What I will do, the next step that I will do is I will just say, let's say that my solutions for the time-dependent Schrödinger equation, I will assume that they are given by this chi plus or minus, no, let's see, c chi plus of t times e to the power e plus I over h bar minus I over h bar e plus, or the integral of this one, from 0 to t, plus chi minus of t e to the power I over h bar from 0 to t e minus of t prime dt prime. Well, if nothing was time dependent, my eigenstates would be just a given such a superposition. Of course, e plus and e minus will also be time independent, and with various coefficients. Now I will also assume that the coefficients are time dependent. And what I'm trying to do is I would like to obtain C plus and C minus. So what the equation I'm trying to solve is this one. So let's see, H acting on chi, H is a spin-off, this is C plus of T. Now, H acts only on chi plus, it only has the magnetic and the Pauli matrices, it doesn't have any derivatives, etc. So it only acts on these states, and that would give me a E plus of T, chi plus of T, e to the power minus I over H bar, 0 to T, E plus of t prime dt prime plus c minus of t e minus of t chi minus of t e to power e minus I h bar from 0 to t e minus of t prime dt prime. This should be equal to the time derivative. Well, let me first write the time derivatives of the exponential. The time derivatives of the exponential just gives me the energies. So c plus of t chi plus of t e plus of t e to power minus I h bar 0 of t e plus of t prime dt prime plus c minus of t chi minus of t e minus of t e to power minus I over h bar 0 to t e minus of t prime dt prime. Plus I have the derivatives of the other parts. So I will have plus c plus dot chi plus c plus d by dt of chi plus multiplied by I h bar times the exponent plus c minus dot chi minus of t plus c minus d by dt chi minus I h bar e to power minus I h bar in the parentheses. Now let's see, there will be some cancellations. This term is cancelled by this one. This one is cancelled by this one. So the terms on the left are cancelled by the first two terms on the right. So I can also cancel these exponents. So what I am left with is dc plus by dt chi plus c plus d by dt of chi plus this plus dc minus by dt chi minus plus c minus d by dt chi minus. This should be equal to 0. I can multiply these with the chi plus bra and the chi minus bra. So I would end up having dc plus by dt if I multiply with the chi plus bra plus c plus chi plus d by dt of chi plus c minus chi plus d by dt chi minus. This should be equal to 0. And similarly, 0 should be equal to dc minus by dt plus c minus chi minus d by dt of chi minus plus c plus chi minus d by dt chi plus. So these are the two equations that I need to solve. Now I need to calculate those matrix elements. I could avoid obtaining what chi plus and chi minus are up to this point, but now I need to find their expressions. And they have to be properly normalized because I already used their normalization. So let's try to find chi plus and chi minus. So this is our V0. And let us write this in this form. This should be h bar omega 1 over 2 minus h bar omega 1 over 2. And the remaining matrix where omega 1 is equal to minus EB0 over M. Omega 1 is a positive, no, omega 1 is negative, sorry. Is the charge of the electron times the magnetic field divided by M. Just a redefinition so that I will not have to write B0 all around.
Negative or positive?
It's negative. It's the charge of the electron is minus E, which is a negative number.
This minus is this number.
Yeah. E we assume to be a positive number. We started with, you see, this is our initial Hamiltonian. In the initial Hamiltonian, we have this minus sign. It's minus B dot mu. So basically we need in fact the eigenstates of this Hamiltonian. This one multiplied with chi plus or minus, or A or B, should be equal to plus or minus. Plus or minus, plus or minus. Well, we factor out all those h bars. This is in fact sigma dot times. This is nothing but sigma dot n hat. This is the unit vector in the direction of B. So since it's the components, it's the eigenvalues of sigma which are plus or minus 1. Now plus or minus A plus or minus B plus or minus. So we have the cosine alpha times A plus or minus plus sine alpha e to power minus I omega t B plus or minus. This should be equal to minus or plus A plus or minus. So this A plus or minus B plus or minus, this is some normalization, times, let's say B is 1. If B is 1, then A is sine alpha minus sine alpha, or let's say A is 1. If A is 1, this is cosine alpha plus or minus 1 divided by minus sine alpha times e to power I omega t. That's B. Now we need to fix the normalization. N squared times 1 plus cosine alpha plus or minus 1 squared divided by sine squared alpha. This is equal to 1. Omega doesn't contribute to the normalization. N squared, so we have 2 plus or minus 2 cosine alpha divided by sine squared alpha. This is equal to 1. So I have sine squared from the square of that parenthesis. I have plus cosine squared, that gives 1. The square of plus or minus 1 is also 1, so that makes 2. So I have twice the cosine alpha times plus or minus 1. And n, I can just choose it to be sine alpha divided by square root of 2, 1 plus or minus cosine alpha. Square root. So we have this A plus or minus, B plus or minus. This is equal to n sine alpha over square root of 2, 1 plus or minus cosine alpha, 1 over 2, multiplied with 1 and cosine alpha plus or minus 1 divided by sine alpha minus sine alpha times e to power I omega t. These are the normalized states. Well, up to now I have always, in the book it's kind of reverse, but I mean, the minus 1 is the ground state. The minus 1 is the excited state, sorry. Or, no, the minus 1 is the, okay, the minus eigenvalue. Let's look at our Hamiltonian. This is the minus of this part. Omega 1 is minus, is a negative number, so this is plus. No, the minus 1 is the ground state.
Now, if it's minus t. No, that's minus. Okay.
So this is equal to 1 over square root of 2 sine alpha divided by 1 plus or minus cosine alpha to the power 1/2, and the numerator is signs just cancel, and I have square root of 2 is outside. Okay, so let's see. So let's see, if we have the positive sign, I have the square root of 1 plus cosine alpha square root divided by minus 1. If I have the minus sign in both places, then I get the minus square root, so it's minus plus. Or with the minus sign corrected, this is plus minus. This is always plus. No, plus or minus. These are my eigenstates. And I have e to power I omega t. Now I need to take their time derivatives. So let's see. Chi plus at the time t is 1 over square root of 2 sine alpha divided by 1 plus cosine alpha to the 1/2 plus 1 minus cosine alpha to the 1/2. Now is this correct? Yes. Now we can do a bit simplifications, I suppose. So let's see, 1 plus cosine alpha is 1 plus 2 cosine squared alpha over 2 minus 1. So this is 2 cosine squared alpha over 2. 1 minus cosine alpha is 1 minus sine squared alpha over 2 twice. So this is twice sine squared alpha over 2. So this is equal to, if I take 1 over 2, 1 over square root of 2, in the numerator I have sine alpha divided by square root of 2 cosine alpha, and sine alpha is equal to twice sine alpha cosine alpha. Cosine alpha, they just cancel, and I have a 2 over in the sine square root of 2 from the denominator, so I get a square root of 2 and cos sine alpha over 2. Whereas in the second term I have, 1 minus cosine alpha is square root of 2. No, there's a sign mistake, it should be square root of 2 cosine alpha over 2 e to power I omega t. So probably here I made some sign mistake, because otherwise it won't be normalized. So let me just take the correct solutions So square roots of 2's also cancel. So chi plus of t is equal to sine alpha over 2 cosine alpha over 2 e to the power I omega t, and the other one cosine alpha over 2 sine alpha over 2 e to the power I omega t. Well, are they orthogonal to each other? Well, both of them should be plus. So let's see, if we take their inner product, sine and cosine, in the other one, I should have sine and cosine, so there should be a minus sign. So these are my eigenstates. They are orthogonal to each other, they are properly normalized. Now what do we need is, we need, for example, chi plus of t times the derivative of chi plus of t, which is sine alpha over 2 cosine alpha over 2 e to the power minus I omega t multiplied with sine alpha over 2 cosine alpha over 2 times I omega times e to the power I omega t, which is sine squared alpha over 2. No, sorry, this is 0. Its derivative is 0. So cosine squared alpha over 2 times I omega. Then we have chi minus of t d by dt, chi minus of t, no, chi plus of t. The only difference will be, here we would have chi minus, so we have minus sine alpha over 2
What does
cosine alpha over 2 times I omega. Then we have the one with the plus sign, with the minus on the right, chi plus of t d by dt, chi minus of t. This will be cosine alpha over 2 minus sine alpha over 2 times I omega. And finally, chi minus of t d by dt, chi minus of t. So this will be minus sine alpha over 2 times minus sine alpha over 2 times I omega. The second and the third, they should be opposite conjugates. D by dt is not Hermitian. I times d by dt, if you define some kind of a Hermitian property for the time derivative, is Hermitian. Because I times d by dt, you can just replace it with the Hamiltonian effect. So the second and the third, they are the same. So they are, since they are purely imaginary, they are the negative complex conjugate of each other. That's no problem. Okay, now, so here we go. we have these differential equations that we need to solve. So let's start with the first one, derivative of C plus. This is equal to 0. So dC plus by dt plus C plus, the matrix element plus matrix element is cosine squared alpha over 2. Well, in fact, you see, all of these are time independent, the matrix elements. So let's just give them some numbers. So this plus matrix element, let's just call them I omega C squared. It's the cosine squared. Plus C minus. Plus minus matrix element, it is minus I omega CS. This should be equal to 0. Alphas are constant. Alpha is the angle that the magnetic field makes with the z-axis. Then the C minus matrix element. Equation for C minus. So we have dC minus by dt plus C minus. Okay, minus is I omega S squared plus C plus is, well, minus plus matrix element is minus I omega CS. This is equal to 0. So this is one equation we have. This is the other equation we have. So how do you solve these? So basically, d by dt of C plus C minus plus some matrix I omega C squared S squared 0 0 C plus C minus plus, or even I omega minus CS minus CS C plus C minus. This is equal to 0. So this is our equation that we need to solve. Do you know how to solve this equation? It's a matrix equation. Well, one possibility is just saying C plus C minus is equal to e to power minus I omega C squared minus CS S squared times T. C plus C, this is at the time T, this is at the time T is equal to 0. This is one way, or another thing, you just assume that C plus and C minus have the same value. Most of the ways that to solve this equation will amount to this one. Just diagonalize that matrix C squared S squared minus CS matrix, diagonalize it, and you have uncoupled equations for the eigenvectors. Okay, let me just copy the result. So that will be the interesting part. So let's assume that C plus at t equal to 0 is 1. C minus at t is equal to 0 is 0. And you can solve all these, and you end up having chi of t, chi minus at t, matrix element squared. This is equal to omega over lambda sine alpha sine lambda t over 2, where lambda is omega squared plus omega 1 squared plus 2 omega 1 cosine alpha. So we started with the plus solution, and this is the probability that we will observe it in the minus solution. We started with a spinner that is pointing in the same direction as the magnetic field, and as the magnetic field is changing in time, this is the probability that we will observe it in the opposite direction. Well, a adiabatic theorem states that this should be 0. But a adiabatic theorem is valid only if the precession frequency, which is omega, is small. Small meaning that much less than the characteristic frequency of this problem, which is omega 1, the energy level, energy spacing. If this is satisfied, lambda is around omega 1, and omega over lambda much smaller than 1. And you see that the matrix the translation probability is proportional to omega over lambda. This is basically the statement of the adiabatic theorem. So in the limit that the change happens very slowly, the transition probability is 0. And again, we see this over here. Well, we can also look at the other extreme. We didn't discuss the other extreme up to this point. I mean, there's not much to discuss. If this is the adiabatic limit. If omega is much larger than omega 1, so it changes very fast. That means lambda is around omega, chi minus of t, chi of t squared. This is approximately, we have the sine alpha, sine lambda t over 2, or lambda is omega t over 2. Well, basically, this states that things don't change. You see, the thing is, this chi minus of t is the eigenvalue pointing in the opposite direction to the magnetic field. So that is changing very fast. So chi of t basically doesn't change. So this is the statement. Now, in fact, I mean, the opposite extreme of the adiabatic limit is that you change the potential fast. So basically, the wave function doesn't change during that change. Not necessarily from here, but the proof of that one is basically easier, let's say, because the time evolution of any state, psi at t equal to 0, is given by e to power minus I over h bar h dt prime from some t up to large T. This is the psi at the time t. Or let's say in the interaction picture, this will be hi. That's the change in the Hamiltonian, h prime I. So if something changes very fast and then stops changing, so we have this well, the wall from here to move straight to the, let's say, twice the length. Well, basically h prime over here is non-zero only in a very small time interval. So the wave, during this change, let's say, t equal to 0 is the time that the change begins, and the t is the time that the change ends. But that means it's from 0 to t of h prime I dt prime, this is almost 0. because h prime is, it can be changing fast, but it is finite. If it is finite, if you integrate a finite function over a very small interval, the result is very small. So at the end of this chain, the wave function practically doesn't change. Of course, after that, it will no longer be an eigenstate, so it will keep evolving, it will keep changing, but during the change in the potential, during the time that you move your wall from here to there, which is fast, your wave function doesn't change. The other extreme, if you move the wall very slowly, the changes in the wave function follow the change in the potential, such that if you start with the nth state, it will always stay in the nth state. If you move it fast, initially, if your wave function is like this, after you move, your wave function is still like this. So it's a superposition of all the eigenstates of your new Hamiltonian. And it will not be an energy eigenstate anymore, and it will start evolving in time.
We think of this as a somewhat inertia.
Inertia of the wave function.
Yes.
Well, I mean, I would rather call it the continuity in time evolution. It's continuous. The time evolution is continuous. Even if the Hamiltonian changes fast, the time evolution should be continuous. Yeah, I mean, if you want to call it inertia, but I would rather keep the concept of inertia to other places.
Now it's much clearer to see it as a gate and universal.
Yeah, okay.
So similar to moving the piston.
It's the moving the wall. The wall is the piston. Other questions? There's still one more concept in this adiabatic processes, so-called the Baire phase. And, well, that we will do on... I mean, will you be here on Tuesday? Will you be here on Tuesday? Okay, so we will be covering it on Tuesday. And on Friday, we can do some more examples. Questions?